Okay, so there are three different states of matter, right? Solid, liquid, and gas. These are the general. And there are, in thermodynamics, we study an equation of state that relates the parameters or the variables that control the equation of state. What are those parameters? What are those variables? Remember Gauss, the gas laws. What were the parameters? What were the different variables that are very important to define the equation of state? Temperature is one of them, very important. What else? Volume and? Number of molecules is one, number of moles, and pressure, right? P, V, T, and N. So these are the important ones, right? If we assume just number of moles equal to 1, then we have P, V, and T. In the ideal gas law, we have PV is equal to nRT. This was the gas law. We get those gas laws from this is the ideal gas law, but we get that ideal gas law from individual laws. And what were these individual laws? Charles' law, Boyle's law, right? Some of these try to see the effect of pressure on the volume at constant temperature. We can also see the effect of temperature on volume, keeping the pressure constants, and all of that, right? So Charles' law, Boyle's law, the derivation of the Kelvin scale, and all that, right? That we studied in geochem. In here, what do you think in our discussion will be the two most important parameters that will control the state of matter? For example, if you are trying to think about whether water will be stable on the surface of Earth or not, what are the two parameters that are most important to study? What will be the phase of liquid or water on the surface of Earth? Between all these, P, V, and T. And? Yes. The volume is also important, but the temperature and pressure are the two most important parameters using which we can see a lot of things about the phases of matter. Okay, so we will study something called a phase diagram in which we vary the temperature, vary the pressure, and then try to understand what is the effect of these two on the state. Okay, we can have PV phase diagrams. We can also have VT or PT phase diagrams. So we are going to see the PT phase diagrams at not considering the volume. We can also have VT diagrams and PV diagrams. Okay, for our things, we'll just look into pressure on the y-axis and temperature on the x-axis, something like this. Okay, temperature on the x-axis and pressure on the y-axis. And then how these diagrams are being created is this: you fix a temperature, fix a pressure, and then see what is the phase of that compound or of the material that you're looking at. Okay, do this for different kinds of pressures, different kinds of temperatures, and then you can kind of see regions in which you will have a gas, regions in which you have a solid, and regions in which you have a liquid. Okay, and this will make sense when you have a huge amount of temperature. So whenever you are thinking about these kinds of PT diagrams, try to look into the extremes first. Okay, look at really low pressures and really high temperatures. What do you think the form of that matter will be? Don't look at this. Think low pressures and high temperature. What will anything want to be like? Solid, liquid, or gas? It will be at gas, because at a low pressure you can just move around more freely, and at higher temperature you have more energy to move around, so it will be gas. Go into the other regime, low temperature but high pressure. solid. So we have low temperatures and high pressures. You are trying to combine everything into one small space. So low temperature and high pressure, so everything will be that solid. And anywhere in between, you will have that liquid phase. Okay? Now, not necessarily that you will be able to go from, from solid to, you can go from solid to liquid, you can go from liquid to gas. And these are the different processes that you are looking at. So just focus on one of these lines. Let's focus on the melting line, okay? Any line that is parallel to the y-axis, what does that signify? What is a constant here? The pressure is constant, right? So at a constant pressure, what are you going to do? What are you increasing? The temperature. So when you're at a constant pressure where you're increasing the temperature and the phase goes from solid to liquid, we call that thing melting. The opposite is called freezing. Make sense? In here, the similar thing. From liquid to gas, you are vaporizing, and the opposite is condensation. Okay? But not only from solid to liquid to gas, at really low pressures, there is no stopping of a solid to go from solid to a gas phase without getting into the liquid phase. Can you give me an example of this thing happening in nature? In which you can go directly from the solid to the gas without encountering the liquid phase. An example of a natural process that does this. Or any compound that does this. Does ammonium chloride do that? Okay. Do you guys know about camphor? Naphthalene? Naphthalene, white naphthalene balls. They will do these things, in which you can directly grow from solid to liquid. Give me another example that you learned in chemistry of the solar system, in which you saw this thing happening. Think about an ice cream that you guys like to eat. What was that? So the Dippin' Dots, right? So that is what is happening. So like when you go, the reverse, we have seen these things happening in reverse, in which you have a gaseous nebula, a solar nebula that is gas at a very low pressures, 10 to the power minus 4, 10 to the power minus 5 bars, 10 to the power minus 4 ATMs. When it cools down, it doesn't go into the liquid phase. It goes directly from this gaseous nebula to the minerals. And these are the chondrites or the chondrules that are forming, right? In carbonation, in chondritic meteorites, the chondrules, this is what is happening, the deposition. Okay, so this is a phase diagram that is very helpful to know what are the phase changes that are happening. So this can tell you many things. Depending on a pressure and temperature, you can actually tell what is the phase of that compound and how these different things what are the different phase change reactions that can happen. Okay, so these are physical reactions. Okay, now this is the phase diagram of water. Very similar, right? Where do we stand on the surface of Earth? At around, so this is 100, so somewhere in here, somewhere between 0 to 25, 0 to 100 degrees Celsius, maybe around this, right? And pressures of 1 atm. So what is a phase? Liquid phase. Now if you go to 100 degrees Celsius, at that 1 atm, you start boiling. So this will boil. When you lower down, this will freeze. So you are going into this because we are at these pressures on the surface of Earth. When you go to more or less, you can change these phase changes, right? Simple, all right? Okay. This is a very simple phase diagram of water. What is unique about this phase diagram of water? Or what change did you see from the previous diagram? Huh? The supercritical fluid, yes. So what is a supercritical fluid? So there is a temperature and pressure region. So this is a PT plot. This is a PT region, right? In which the phase of water is such that it is difficult for you to differentiate whether it's a liquid or a gas. That is a supercritical fluid. This can also happen in carbon dioxide. In these supercritical conditions, things become really reactive. So there could be more reactions happening, technically. But given, there are some caveats to that, but you can think of it at that. But the major thing is, you will not be able to differentiate between whether it's a liquid or a gas. Similar to that, in this region, everything is gas. In this region, everything is liquid. In this region, everything is ice. But on this line, what is the nature of water? What is the phase of water on that line, on this line? What is the phase? Is it liquid or is it gas? Or neither? Or both? It is both. So water at this PT condition, and if you vary that, it will be both liquid and gas. Similar to this, it will be both liquid and ice. Say you get an iced drink. At 0 degrees Celsius, at the normal atmospheric conditions, you will have both ice and liquid water stable. Right? You can see that, right? And in these, you can also see that the vapor and the liquid both are coexisting. Right? So similar to that, you can find out that at these high temperature and pressure conditions, that becomes a supercritical fluid. But there is one more very typical thing that is happening in here. Let me ask you a question. What will be the nature of a compound when I apply more force to it or more pressure to it? Will it try to go from solid to liquid or liquid to solid? You are putting more pressure. So what is happening? The things are getting closer or farther away? Closer. So there should be a tendency of going from liquid to solid. Right? So when you apply more pressure, you should go from a liquid to solid. Things are different with water. And this is, you can see this in this melting curve, which has a negative slope. Let me show you in here. In here, what is happening? We have a positive slope. In here, you have a negative slope. Just think of it as this. In here, when you have, say, you have a solid in here, and you increase the pressure, it stays as solid. In here, you increase, so if you are a liquid, you increase the pressure. You kind of go into the solid region. But it is the opposite. You are a solid in here, you increase the pressure, it becomes liquid. And that's what happens in ice. So you have ice, you put some pressure on it, the ice starts to melt at the base. That's what happens in glaciers. That is why glaciers move. Because at one point of time, glaciers, which is made up of water ice, becomes so heavy that the pressure at the bottom becomes so high that this becomes liquid. And that is only happening at that interface. And then the glacier starts to move. This will not happen with any other thing. The other impact of this is, ice is less dense. Right? And this is not just this thing playing a part, but also hydrogen bonding plays a huge amount of part. But the densest that water can get is at 4 degrees Celsius and not at 0 degrees Celsius. So if you have a liquid that is at 10 degrees Celsius, you lower the temperature, it becomes more dense. So colder it becomes, the more dense it becomes. 6 degree, 5 degree, 4 degree. But when you cool it further down, the density decreases. It's unique. We'll look into how that functions sometime in detail, but not here. But that's another. And this unique behavior is being represented by this negative slope. Okay, this is unique. Most things will have a positive slope in here. Okay, so you can also see an application of the phase diagrams on the surface of Mars. So this is an image taken by the Phoenix lander in 2008-2009. Okay, so the Phoenix lander was a NASA lander mission that landed in the Vastitas Borealis region on Mars. Okay, and what it did, it scooped a little bit of that surface dust cover out. And so this is Sol 20. Sol is a Martian day. So in Sol 20, when it scooped, you could see these white looking things. Take a guess what these were? It could be a salt, it could be ice, but it was an ice. Okay, there was also salts in it, but this water, this ice looking, this white looking thing was water ice. You come back 4 days later, you can see that these whites were kind of not there. So what was happening is this ice that was stable was now not stable. So given the PT condition, pressure temperature condition on the surface of Mars, ice was evaporating or sublimating actually. So you have solid sublimating into, it's not becoming water, we don't see that, but it is sublimating into water vapor. Okay, so we could see this. And so this is a really complicated, well-detailed diagram of the PT diagram for water, and you can see that these were the Martian conditions. Okay, so when you have the Martian conditions, so water, H2O, can only be stable as ice on the surface, and when the temperatures increase, you will become vapor. When you decrease the temperature, you become ice, and that's what happens on Mars. You don't get into the liquid phase because the pressures are so low. So if you increase the pressure, then it can go through this. That's what happens on Earth, but not on Mars. We are in this region. That's why we do not see, and this is pure water, but liquid water can become stable if you have salts in it. That's what we were doing during the ice storm, right? Salting the roads to depress the freezing point of water. And we will take that. That's a different discussion. But phase diagrams are very important. Okay. Now, this is what we saw. Like the phase diagrams were different for most materials and for water. The direct impact are as we noticed. Now, since ice is less dense than water at 4 degrees Celsius, when a lake freezes, it only freezes on the top. The rest of the water is maintained at what temperature? 4 degrees Celsius. So whatever the temperature on the outside, the water inside is 4 degrees. That's just amazing. So that is why the living creatures that are in those lakes can survive because of the dissolved oxygen that was there. Okay, this is a miracle of life, right? That water does not freeze at 4 degrees Celsius because it has hydrogen bonding. Okay, the unique properties of water is what makes water uniquely suitable for life, like for supporting life. Okay, we can think about other liquids, but we need to find liquids with such unique properties for the type of life that we are used to. For Titan, for example, you can have a methane and ethane, but ethane and methane does not have hydrogen bonding. So a thing like this will not be possible. So if it freezes completely, or freezes the opposite way. So it starts to freeze, and there is a possibility that the entire thing could be frozen. So what will happen to the life if there is a methane lake or an ethane lake on Titan? You don't know. Okay. Interesting things. Now, while the most important or most common forms of life that we see it are solid, liquid, and gas, there are we will discuss about two different forms of states of matter that occur in extreme conditions. One is plasma that occurs at extremely high temperatures. Why is this important? Because most of the matter that we have in the universe is plasma because of the temperatures. All these stars that we have, all that is plasma. At those high temperatures, so any gas, you take any gas and subject it to high temperatures, what you are actually doing is giving more and more energy to that gas. When you push more and more energy into that gas, what you're actually doing, what are you doing when you are giving more energy to a gas? Say a hydrogen gas, very simple. You have a hydrogen gas. You give more energy to it. What will happen to that hydrogen atom? Sorry, what happened?
Go further.
So what is a hydrogen atom? What is it made up of? Yes. So when you give energy, what is the thing that takes that energy? The electron takes the energy. What happens then?
It can emit it from the...
If you remember the atomic structure, we have different shells, right? Each shell has a particular energy, right? This is called the quantization of energies. Yes. So each shell has a fixed energy. So the first shell of hydrogen has a fixed energy. The second shell of hydrogen has a fixed energy. The third shell of hydrogen has a fixed energy, and so on and so forth. Although these shells are not filled, but they do have these shells. Okay? So the first shell has, believe me, that it has the energy of minus 13.6 electron volt. What does the minus signify? It is more stable. Right? So, how these energies are demarcated is the energy at infinite distance from the nucleus has an energy of 0. Okay? So, imagine that I'm the nucleus. Okay? If an electron sits very close to me, will it be more stable or when it stays far away from me? Think about the electrostatic forces. The electrostatic force is what? K times Q1 times Q2 over R squared. Like this was the energy. Right? Very similar to gravitational. The R is the distance. So as you increase the distance, the energy will be less. So you are more stable when you are sitting right next to me. That is why the energy will be less and less. The minus sign is showing what? It's showing an attraction. Because the plus and the minus is attraction force. So attraction forces are always what? Stable. So the closer you are more stable. So you are minus 13.6 electron volt when you are sitting in the first shell. You are minus 13.6 over 4. And this is what the energy of the nth shell is minus 13.6 z square over n square. I'll write it here. Minus 13.6 z square over n square in electron volt. Z is the atomic number and n is the nth shell. For hydrogen, Z becomes 1. So this becomes minus 13.6 over n squared. For the first shell, Z is 1, N is 1, so minus 13.6. For the second shell, Z still remains 1, N becomes 2, so the energy of the second shell becomes what?
13.6 upon
4, which is 3.4 or something like that, right? Minus 3.4, and so on and so forth. You can calculate any of the shells. But the idea is you have the least energy here, least energy more stable, right? And then you keep on increasing the energy. And when you are at infinite distance, you are at 0. Okay? This is the logic. So when you have the first electron sitting in here and you give it energy, what will it do? It will take that energy. Can it stay in that same electron? No. In that same shell? No. It has to jump to a higher energy state, a higher orbit. So if the final energy of the electron becomes 3.4, it will go to the second shell. If it becomes equivalent to the third, then it goes to the third cell, right? And so on and so forth. This is extremely important. So every atom will have a fixed energy for its first shell, second shell, third shell, fourth shell, so on and so forth. This will be true for all the atoms, okay? Hydrogen, helium, argon, oxygen, lithium, whatever, okay? Bohr's model of energy, of these Bohr's model of these energy states. That's what we call it, right? So minus 13.6 Z squared by N squared. So now, for example, what is the energy difference between 13.6 and minus 3.4? 10.2? So if that electron gets a 10.2, then it can go to the second shell, and so on and so forth. So this is how the electrons get energy, and they can go and they jump to the different ones. So there has to be a very particular energy that it needs to absorb and then go. Imagine you give it a lot of temperature. And what is temperature? It's a lot of energy, right? Temperature is a measure of energy. You get a lot of that. So these electrons have so much energy that they have left the system and gone away. So there is nothing left now. So not only you gave it minus 13.6, probably you gave it, I don't know, minus 14, minus 15, minus 100, whatever. So not minus, I mean plus of that, right? So it is minus 13.6 and I gave it 14. So it took that energy and went away. What do we call that thing? That process in which that atom becomes an ion. It's the ionization energy. That atom is now ionized. That hydrogen gas is now ionized. The plasma is that, a gas that is ionized. So you have all these highly energetic electrons with the nucleuses. That is plasma. 99% of the mass of the universe is this plasma. So the matter that we see in here is very less. We are not plasma, we are either in solid, liquid or gas form. That is very less. That's why we need to think about this plasma. So this was high temperature. Now, let's talk about, this is the same, let's talk about the other extreme. Let's talk about high pressure. When you subject an atom to high pressure, what do you think is going to happen? Think about these processes. When you're just pushing something in, what will happen to the atom, to the electrons, to the neutrons? What is going to happen? It will get condensed. So we saw in the SPDF configuration, right? So all these electrons were happily residing in these different orbitals, right? Now there was a rule or a law called Pauli's exclusion principle that said, or that postulated, that no two electrons can have the same set of 4 same quantum numbers, and that came down to one subshell cannot have more than 2 electrons. That things starts to get into play in here, because when you are crushing these things in, you are forcing more than